So today we'll continue with Coulomb's law. And what did we saw in the previous classes? We saw that if we have two charges that are opposite to each other in a nature, so one is positive and the other one is negative, then the force is attraction. And if it is two charges that are the same nature, so both are positive or both are negative, then what will happen is that they will repel each other. The addition into that is known as the general law of charges is that if you have a charged sphere and a neutral sphere, always will attract to each other because of the induction that is happening into the neutral charges. And remember what we said, that induction is rearrangement of the charges within the sphere. Now, Coulomb studied his the interaction between the two charges that are static, that are not moving, and this is why the force that they are either attracting or repelling each other is known as the electrostatic force. So electro stands for the charges, and static stands for the fact that the two charges are not moving. Finding that Coulomb's had through this law is that the magnitude of the electrostatic force between the two charges is direct proportion of the product of the two charges Q1 and Q2. Again, what did we say that direct proportion is? Is that if you are increasing one side of the relation at a certain rate, then at the same rate will be the increase on the other side. So if we are increasing the product of the two charges by a rate of, let's say, 2.3, then the force will be increased by a rate of 2.3 as well. Now, if one of the charges is increased by 1.5 and the other one, let's say that one of them is increased by 1.5 and the other one is increased by 2.0, then the product of the two will result into an increase of 3.0, which will result in the increase of the magnitude of the electrostatic force as 3.0. So always we have to see, when we are stating that is direct proportion, we have to see that the side, if the side is increased or decreased by a certain factor, the same effect, either the increase or decrease, will happen on the other side of the relation. So if we have a decrease by a certain factor, let's say a 5.2, 5.5, then the magnitude of the electrostatic force will have the same effect, will be decreased by a factor of 5.5. So this is the first finding that Coulomb had on his experiment. And now the second finding is that the magnitude of the electrostatic force is direct proportion to the inverse of the distance squared between the two charges. So again, what we are saying here is that if this side, the side, not just the distance, but if this side is increased, then the electrostatic force will be increased as well. But if the side is decreased, then the electrostatic force will be decreased as well at the same rate of increase or decrease. When you put those two together, so when you say that is direct proportion of the product of the two charges and direct proportion of the inverse squared of the distance between the two charges, then direct proportion doesn't mean equal. When you make them equal to each other, then you can state or you can find, and this is what Coulomb's found, is that the magnitude of the electrostatic force between the two charges is equal to K, which is Coulomb's constant, Q1, Q2 over R squared, where K is Coulomb's constant, and it is in your data booklet as 8.99 times 10 to the power of 9. And Q1 is the magnitude of the charge 1. So it's magnitude of Q1. And Q2 is the magnitude of Q2. And R is the distance between the center to center of the charges. Distance in meters. So if charges are in coulombs, then distance is in meters. So this constant here is in your data booklet, and you can find that on the attached link that you have on D12. Now, so the problem becomes a bit more quote unquote complicated, because what we are doing now is we are dealing with a vector, but we are finding the direction using the general law of charges, which is saying that two charges that are the same will repel each other, and two charges that are opposite will attract each other. And the magnitude using K, Q1, Q2 over R squared. As you notice, this equation that you see here is very, very similar to the equation that is the universal force of gravity. So when you saw on physics 20, you saw that the magnitude of gravitational force between two objects with mass m1 and m2 is the universal gravity constant, G, m1, m2 over R squared. And the reason for this is, first of all, the law satisfied the interaction between the two, but what it is, at the time that Coulomb was working on the experiment to figure out what is the electrostatic force between the two charges, Newton was one of the most respectful physicists in the world. Therefore, they were thinking that this force, or the format that this force was calculated, was the universal force, and every force should have the same look as the universal force of gravity. However, even at the time that Newton was alive and was very famous, was proven that this is not the way that every force will be, or the form that will be presented. But it happens that the electrostatic force and the force of gravity are very similar in the way that on the form that they are calculating the magnitude. The only difference in the direction is that universal force of gravity is always attraction, is an attraction force between the two masses, and the electrostatic force between the two forces can be attraction or repulsion. And this is dependent on the nature of the charges Q1 and Q2. So now let's see some examples in which we are calculating the electrostatic force that exists between two charges, and then we will see some questions on the direct proportion stuff. So let's suppose that we have charge 1 that is with magnitude 2.83 times 10 to the power of negative 6 coulombs and positive, and charge 2 that is as well positive with a magnitude of 4.85 times 10 to the power of negative 6 coulombs, and they are apart from each other at a distance of 12.3 centimeters. So the situational diagram for this particular example will be something like this. Let's suppose that you have a charge 1 that is on this position, and 12.3 centimeters away, you have another charge that is positive as well, and the distance between those two is 12.3 centimeters. Now, if we are calculating the electrostatic force that charge 1 is experiencing, then in our mind, what we have to do is we kind of have to put ourselves into charge 1, and then based on the general law of charges, ask what is the force that charge 1 is experiencing as a result of the presence of charge 2 being with the same nature. So is it traction or repulsion? Since the nature of the two charges is the same, then the force that charge 1 is experiencing as a result of presence of charge 2 is a repulsion force. So you can say that this is the direction that the electrostatic force that charge 1 is experiencing as a result of the presence of charge 2 will be something like this. Now, how is it? We said it even in the previous class, that you will draw an imaginary line between the center of the two charges, and then along that line, you have to draw the force. And then if we are looking for what is the electrostatic force that charge 2 is experiencing, then what do you have to do is you have to put yourself into the charge 2 position, and then ask yourself, what is the nature of the force that charge 2 is experiencing as a result of the presence of charge 1? Being the same nature charges, the force will be repulsion as well. So along the line that connects the two centers of the charges, then you can draw a line that is identifying as a repulsion, and this is the direction that electrostatic force of charge 2 is experiencing as a result of the presence of charge 1. Now, we very often do not say F21, F12. We just simply say Fe as a result of 2 and Fe as a result of 1. Now, after we find the direction using the general law of charges, as we did here, we will calculate the magnitude of those forces. So the electrostatic force that 1 is experiencing as a result of 2, 1 is experiencing as a result of 2, will be K Q1 Q2 over R squared. Or if we substitute now, will be 8.99 for K, 8.99 times 10 to the power of 9 times 2.83 times 10 to the power of negative 6 times 4.85 times 10 to the power of negative 6 over, let's convert this into meters, times 10 to the power of negative 2, and the whole thing to the power of 2. So any units given for the distance other than meters, then you have to convert that into meters. Notice another thing here, that we do not worry about the nature, to identify the nature of the charges. So we take just the magnitude of charge 1 and the magnitude of charge 2, and we don't worry about the is it positively charged or is it negatively charged. After you enter this in your calculator, you will find that the magnitude of the electrostatic force that charge 1 is experiencing as a result of charge 2 will be newtons. So the magnitude, after you enter it in your calculator, you will have 8.16 newtons. And if you are expressing it as a vector, then the electrostatic force that one is experiencing as a result of two will be 8.16 newtons, and in this case, going west, or repulsion. Even if you are calculating the magnitude of the force that charge 2 is experiencing as a result of the presence of 1, you should have the same value, because see what you are doing. 2 as a result of 1 will be k q1 q2 over r squared, and they are the same thing. So 8.99 times 10 to the power of 9, and then 2.83 times 10 to the power of negative 6, times 4.85 times 10 to the power of negative 6 over 12.3 times 10 to the power of negative 2, the whole thing to the power of 2. So everything is the same, will be 8.16 newtons. And if you are expressing it as a vector, then you will have 8.16 newtons, and in this case will be going toward east. Now, the question that I have for you is, since those two forces are with the same magnitude, 8.16 newtons, and opposite direction, because they are repelling each other, and even when they are attracting each other, will be in the opposite direction. So how come that those two forces do not cancel each other? Even though those two forces are with the same magnitude and in opposite direction, they do not cancel. Those two charges cancel out. Those two charges will experience this force because they are experienced in two different objects. So this force is experienced at charge Q1, and this force is experienced on charge Q2. This is why those two forces do not cancel out. Let's suppose that we have another example in which we are having two charges that are identical. So Q1 and Q2 are identical, with Q1 is equal to Q2 equal to Q. And the magnitude of each of them is, let's suppose, 2.85 times 10 to the power of negative 6 coulombs. And they are apart from each other at a distance of 24.3 centimeters. Let's find the magnitude of the electrostatic force that Q1 is experiencing. So what is the electrostatic force that charge 1 is experiencing as a result of charge 2? So the two charges are both positive. Therefore, the free body diagram in terms of the electrostatic force that charge 1 is experiencing will be a repulsion along the line, that imaginary line that connects the two centers of the spheres, and is a repulsion because the two charges are equal to each other. So this will be the electrostatic force that 1 is experiencing as a result of 2. The magnitude of this force will be calculated as kq squared, q1, q2, since they are equal to each other, then will be q squared over r squared, or 8.99 times 10 to the power of 9 times 2.85 times 10 to the power of negative 6, the whole thing to the power of 2, over 24.3 times 10 to the power of negative 2, converting it into meters, the whole thing to the power of 2. When you enter it in your calculator, the magnitude of the electrostatic force of that charge 1 is experiencing as a result of charge 2 is 1.24 newtons. And if you are stating it as a vector, then it will be 1.24 newtons going west for repulsion. Now let's see a case when we have two charges that are charge 1 and charge 2. And originally, charge 1 is with a magnitude of, let's say, negative 3.82 times 10 to the power of negative 6 coulombs. And charge 2 is with a magnitude of positive 7.93 times 10 to the power of negative 6 coulombs. And they are apart from each other at a distance of 15 centimeters. And what is happening is through a conducting wire or placed in contact with each other, the charges are connected and then they are placed at the original position. So a conducting wire is connecting those two charges, or two charges 1 and 2 are placed in contact with each other, and then after they are placed in contact, they are in their original position, meaning that they are 15 centimeters apart from each other. What is the electrostatic force after they are put in contact with each other and placed 15 centimeters away from each other? In order to approach this problem, what we have to do is we have to find the new magnitude of the charges after they are in contact with each other, because what is happening will be that the two charges will be redistributed based on the general law of charges. So the two new charges, prime, are equal to each other, and they are equal to the average of the two original charges. So we'll have negative 3.82 times 10 to the power of negative 6 plus positive 7.93 times 10 to the power of negative 6 divided by 2. And after you enter them in your calculator, you will find that the new magnitude of the two charges 1 and 2 will be equals to, positive 2.06 times 10 to the power of negative 6 coulombs. You can keep it as 2.55 times 10 to the power of negative 6. It's fine. Now, what you have to do is you have two charges now, Q1 and Q2, that are equal to each other as positive 2.06 times 10 to the power of negative 6, that are apart from each other 15 centimeters. If we are calculating, let's say that we're calculating the electrostatic force that 2 is experiencing, then what we will do is we will place ourselves at charge 2 and then say, what is the nature of the force that charge 2 is experiencing as a result of the presence of charge 1 being the same charges as a repulsion. So the free body diagram of the electrostatic force will be something like this: 2 experiencing as a result of 1, and the magnitude of it is calculated as K Q1 prime Q2 prime, which they are equal to each other, over R squared, or 8.99 times 10 to the power of 9 times 2.06 times 10 to the power of negative 6, the whole thing to the power of 2, over 15 times 10 to the power of negative 2, the whole thing to the power of 2. And whatever the calculator gives you, then you will state the force. Now, if we consider the Coulomb's law, what we said, that electrostatic force, the magnitude of the electrostatic force is K Q1 Q2 over R squared. From here, we can derive that the distance, if we know what is Q1, Q2, and the magnitude of the force, we can derive that the distance will be the square root of K Q1 Q2 over magnitude of the electrostatic force that exists between those two charges. So if you know the nature of the charges and you are finding the distance between the two, knowing the force that they are experiencing, then you can use this formula. This formula is not on your formula sheet. On your data booklet is only this is the formula that is on your data booklet, but you can easily generate this formula, or if the two charges are equal to each other, then electrostatic force will be kq squared over r squared, as we saw in the previous example. And if we derive what is the magnitude of the charge, then we can say that the magnitude of the charge is the square root of the magnitude of the electrostatic force times the distance squared over K. Again, this formula is not in your formula sheet, but you can use this formula if the question is asking you what is the magnitude of the charges, knowing the distance and the electrostatic force. Now we'll see some questions that are related to the direct proportion in terms of the electrostatic magnitude of the electrostatic force. So let's suppose that originally what we have as a result of the magnitude of Q1, Q2, and a distance, and they are all original, then we have an electrostatic force that is with a magnitude of, let's suppose, 5.6 newtons, and we're just stating the magnitude. And now what we are doing in the new situation, we are changing the magnitude of charge 1. We are increasing it with a factor of 2.3 in relation to the original magnitude of the charge 1. And we are keeping everything the same. So Q2 new is the same as Q2 original, and the radius nu is the same as the radius original. And now we are asking what is the magnitude of the electrostatic force in the new situation. Now, we will complete this, or we will approach those questions in this way. Based on the Coulomb's law, we can say that for the original situation, this 5.6 is as a result of the product K, Q1, Q2 original over distance original squared. And the new situation, based on Coulomb's law, will be as a result of the product of K, Q1 new, Q2 new situation over the distance nu to the power of 2. Now, what do we have as a given is that charge 1 in the relation to the original situation is K is constant. Charge 1 is 2.3 charge 1 original. Charge 2 is the same as the original, and the distance is the same as the original. So now, what do you have here is when you take K, Q1 original, Q2 original over R squared original, then you will have the new force, the new electrostatic force will be 2.3 that is left from this circle that I made here, or this loop that I made here, times the electrostatic force original, because K, Q1 original, Q2 original, over R squared original is equal to the original electrostatic force. So this will be the same as saying 2.3 times 5.6, and the new magnitude of the electrostatic force that after we are increasing charge 1 only by 2.3, increasing it by a rate of 2.3, will be 12.88 newtons. Now let's see a case when what we are doing is we are changing both charges. One is increased, the other one is decreased, let's suppose. So for the original situation, we will have Q1 original, Q2 original. We don't worry too much about what is the exact value. And then we will have an electrostatic force original at, let's stick with 5.6 newtons. Okay, I'm having a phone call and I need to take this. So can you please have a 5 minutes break for me? And as the original position or original situation, what we have is charge 1 is, let's say, decreased by a factor of 1.5. So when you have decrease, then it is dividing it by that number. And charge 2 nu is an increase of a factor of, let's say, 3.2 in the relation to the charge 2 original, and the distance is not changing, and we are looking for what is the new electrostatic force. Now again, the original electrostatic force is K, Q1 original, Q2 original over the distance original squared. While based on the Coulomb's law, the new electrostatic force can be calculated as K, Q1 nu, Q2 nu over the distance nu squared. Let's plot now what do we have here. For the first, constant will stay constant as it is. For the new charge, we'll have Q1 original divided by 1.5. For the new Q2, we'll have multiply 3.2 by Q2 original over the distance is the same, so R squared. And now see what do we have? Q1, Q2, and distance. The product of K, Q1, Q2, and divided by the distance will be the original force, which is equal to 5.6 newtons. And then as a leftover, after you take away K, Q1, Q2, and R squared, you will have a new electrostatic force as 3.2 over 1.5 times the original, which is given to be 1.5 times 5.6. So the new electrostatic force will be whatever is the result as 3.2 divided by 1.5 times 5.6, and will be 11.95 newtons. On the last example, when we are dealing with this proportional, is when we have the distance changing. It is unique, so therefore what I will do is I will just take that quantity changing, not dealing with the charges. So for the original situation, we have Q1 original, Q2 original, and the distance original. And as a result of the combination K, Q1, Q2 over R squared, we will have an electrostatic force. Let's stick with 5.6. And then as the new situation, we'll have Q1 new is equal to the original, Q2 new is equal to original, and the distance is, let's say, that is increased by a factor of 2. What is the new electrostatic force? So based on Coulomb's law, the original electrostatic force is K, Q1 original, Q2 original over radius original squared. As well, for the new situation, we'll have Q1 new, Q2 new over the distance new squared. Now, based on what we said, the Q1 new and Q2 new are the same. So the new force will be Q1 original, Q2 original over, now the distance is doubled, so 2 the original distance squared. The mistake that the students do on this case, and this is why I'm doing only this case, only this change, is that they don't use the brackets, because this to the power of 2 is affecting the factor in which the radius is changing and the r to the power of 2. So this will be the same as saying K, Q1 original, Q2 original over 4, because 2 to the power of 2 is 4, distance original squared. And then, based on what we have here, this force or this combination of K, Q1 original, Q2 original over radius original squared will give us 5.6. So the new electrostatic force will be 5.6 divided by 4, or if you enter it in your calculator, will be equals to 1.4 newtons. So let's suppose that we have, as the original situation, you have Q1 original, Q2 original, radius original, and then as a result of combination of those three, we have 5.6 Newton magnitude of the force. As the new situation, I will keep those the same just to be focused on what is the most common mistake the students do is, let's say, that is decreased by a factor of 3. So decreasing means dividing, and we are looking for the electrostatic force on the new situation. What is the magnitude of it? Again, we'll start same as we did with electrostatic force in the original situation, K, Q1, Q2 original over original squared, and the electrostatic force nu will be K, Q1 nu, Q2 nu over the distance nu to the power of 2. Now, if you have a change on the charges, then you will plot that change there. If it is increasing, multiplying. If it is decreasing, then dividing. On this case, just to keep it simple, I'm not expressing any change on the charges. So this will be the original for the distance, divide by 3, the whole thing to the power of 2. Now this to the power of 2 is affecting the distance and the over 3. So this will be K, Q1 original, Q2 original over distance to the power of 2, the whole thing to the power over 9. Because 3 to the power of 2 is equal to 9. So see now, what do we have? We have this that is equal to 5.6. So the electrostatic force mu is 5.6 over 1/9. When you divide two fractions, you save the first fraction, convert dividing into multiplying, and you flip the second fraction. So it will be 9/1. And then when you enter this in your calculator, you will have a magnitude of 50.4 newtons. This is the first part of Coulomb's law. We will see more examples on the other